And the final topic in Chapter 4 is the titration. Titration is a common laboratory method of quantitative chemical analysis, and this is used to determine the concentration of an analyte. Since volume measurements play a key role in titration, it is also known as volumetric analysis. The titrant, or a reagent solution of a precisely known concentration, is added to the analyte in a titration. An indicator, or an acid-base indicator, changes color depending on the pH of the solution. We can also use redox indicators. What happens is we add a drop of indicator solution to the titration at the beginning of the reaction. And when the endpoint has been reached, when the color changes. Now, the endpoint is an indicator of the completion of the titration. And this is detected by some type of physical change produced by the solution. For example, a color change. The endpoint typically comes straight after the equivalence point, which is when the moles of a standard solution, your titrant, is equal to the moles of a solution of the unknown concentration. This is your analyte. So the ideal point for the completion of a titration. In a perfect titration, the endpoint and the equivalence point are identical. One of the most common titrations is an acid-base titrations, and we do this to determine the concentration of an acid or a base by exactly neutralizing the acid or base with an acid or base of known concentration. The goal of the titration is to determine the concentration of an unknown analyte by reacting the analyte with a standardized solution of known concentration. The volume of titrant reacted is called the titration volume. A typical titration begins with a beaker or Erlenmeyer flask containing a very precise volume of the analyte and a small amount of indicator. In this example, we use phenolphthalein. Phenolphthalein is used because it's clear colorless in an acidic solution and this pretty pink color in a basic solution. The standard solution is placed in a burette, this long tube shaped thing, and small volumes of the titrant are added from the burette to the analyte in the indicator solution. And we do this until the indicator solution changes color. The point or volume in which the indicator changes color is the endpoint of the reaction. When the endpoint of the reaction is reached, the volume of titrant used is measured. And with this information, we can calculate the concentration of the analyte. Let's go through this example of an acid-base titration. And for this problem, we're going to use dimensional analysis and stoichiometry. So I have the reaction of 2 moles of potassium hydroxide reacting with 1 mole of sulfuric acid. And this produces 1 mole of potassium sulfate and 2 moles of water. The question states if 40.8 milliliters of a 0.106 molar sulfuric acid solution neutralizes 50.0 milliliters of a potassium hydroxide solution, find the concentration of potassium hydroxide. Our path here is to convert milliliters of sulfuric acid to liters of sulfuric acid. Once we do that, we can use the molarity of the sulfuric acid solution to convert to moles of sulfuric acid. This cancels liters of solution, and you're left with moles of sulfuric acid. And to convert to moles of sulfuric acid to moles of potassium hydroxide, we use stoichiometry. The valence equation tells us that we need 2 moles of potassium hydroxide to react with 1 mole of sulfuric acid. So our next term in this calculation, we want to cancel moles of sulfuric acid. So we use the mole ratio from our balanced equation, 2 moles of KOH divided by 1 mole of sulfuric acid. This cancels moles of sulfuric acid, and this gives us moles of potassium hydroxide. If we put this all in our calculator, we get moles of potassium hydroxide to be 0.00865 moles. Now our question in our problem was asking the molarity of potassium hydroxide. Our given says that we have 50.0 milliliters of potassium hydroxide solution. Now, molarity is defined as moles per liter. So before we can move forward, we need to convert the 50 milliliters of potassium hydroxide to liters. So we can set up our calculation as 0.00865 moles of potassium hydroxide divided by 50.0 milliliters of potassium hydroxide solution. And here's where we convert milliliters to liters. We know that 1 liter is equal to 1,000 milliliters, so we divide 50.0 milliliters by 1,000 milliliters. Putting this all together in our calculator gives us 0.173 molar potassium hydroxide. And that's the molarity of our potassium hydroxide solution. Now in this next slide, we're going to go through a different type of titration reaction. Titrations don't have to be acid or be acid-base reactions. They can also be a redox reaction. Let's go through a redox titration problem. We have 10 milliliters of an iron 2+ solution, and that is titrated with 20 milliliters of a solution containing the permanganate ion. And this permanganate ion solution has a concentration of 0.02 molar. Determine the molarity of the iron 2 solution. And the balanced equation for this reaction is 1 mole of the permanganate ion reacts with 5 moles of the iron 2+ ion and 8 moles of H+ ions. And this forms the manganate 2+ ion, 5 iron 3+ ions, and 4 water molecules. Let's take a look at our given and our find. Our given is 10.0 milliliters of iron 2+ and 20 milliliters of the permanganate ion and 0.02 molar permanganate ion. And our find is the molarity of iron 2+. Our approach to this problem is to use dimensional analysis and stoichiometry, as well as the definition of molarity to find our answer. First, we convert milliliters of the permanganate ion to liters. Then, using the molarity of the permanganate ion, we convert to moles of permanganate. We then use stoichiometry to convert from moles of permanganate to moles of iron. And lastly, we use the moles of iron and the volume of iron solution used to determine the molarity of the original iron 2+ solution. Okay, so we're given 20 milliliters of the permanganate ion. We need to convert this to liters by dividing by 1,000 milliliters for every 1 liter, and that cancels milliliters. Now we convert to moles of the permanganate ion by multiplying the molarity of the permanganate ion, which is equal to 0.020 moles per liter. This cancels liters. Next, we use the balanced equation to convert from moles of permanganate ion to moles of iron. So we have 1 mole of permanganate for every 5 moles of iron. And we use the mole ratio, 5 moles of iron 2 divided by 1 mole of permanganate ion. And that cancels moles of permanganate. So our solution has a 0.002 moles of iron 2+. Now we need to determine the molarity of our solution. Remember that molarity is moles of solute per liters of solution. We have 0.002 moles of iron 2 plus and 10.00 milliliters of solution. So to set up our equation, we divide 0.002 moles of iron by 10.0 milliliters, and 10.0 milliliters is divided by 1,000, and that gives us 0.200 molar iron 2 plus, and that's our answer.